When faced with an infinite series, we cannot manually calculate an infinite number of terms. So how do we know if it settles on a finite number or expands into infinity? Our gold standard is the geometric series. If the ratio between terms is strictly less than 1, it converges. This behavior powers two analytical tools, the root test and ratio test. Both force a complicated series into a direct comparison with a simple geometric one. If we can extract a growth factor from our complex series and prove that it shrinks at a comparable rate, then we mathematically lock in our convergence. Let's look at the formal definition of the root test. Here in Walter Rudin's Principles of Mathematical Analysis, the defining equation sets a variable, alpha, to the limit superior of the nth root of the nth term. Using the limit superior instead of a standard limit allows us to handle wildly oscillating sequences. The theorem outlines three distinct outcomes. If alpha is strictly less than 1, the series converges. If alpha is strictly greater than 1, it diverges. And if alpha equals exactly 1, the test gives no information. That boundary of exactly 1 is inconclusive because multiple behaviors can exist there. Take a look at this side-by-side plot. On the left is the harmonic series, which climbs to infinity and diverges. On the right is the inverse square series, which settles to a finite sum and converges. If you apply the root test to both of these equations, they both yield an alpha of exactly 1, making it impossible to distinguish between them using this tool alone. Next is theorem 3.34, the ratio test. Instead of taking an nth root, this test analyzes the immediate multiplier required to step from one term in the sequence to the exact next term. While both tests hunt for a geometric growth factor, they extract it differently. The root test evaluates the aggregate behavior of the nth term, while the ratio test measures the localized distance of a single step. This brings us to a direct competition between the two tests. Rudin provides a specific alternating denominator series in example 3.35 to demonstrate what happens when we apply both methods. Try to mentally apply the ratio test here. Because the denominator alternates, the step from an even index to an odd one produces a wildly different ratio than the step from an odd index to an even one. As a result, the limit inferior drops to 0, while the limit superior shoots to positive infinity. The ratio test breaks down entirely because its limits span past the boundary of 1. But if we apply the root test to the exact same series, the limit superior resolves cleanly to 1 over the square root of 2, a number strictly less than 1. The root test conclusively proves convergence where the ratio test fails. Theorem 3.37 formalizes this mathematical advantage. Look at the inequality chain here. The limits of the root test are mathematically squeezed inside the limits of the ratio test. Because the root test's boundaries are strictly tighter, anytime the ratio test shows convergence, the root test will too. However, as we just saw, the reverse is not true. The root test has a definitively wider scope. This scope becomes particularly useful when we introduce power series. By applying the root test directly to the coefficients of a power series, we derive the formula for the radius of convergence, denoted as r, which is simply 1 over our root limit alpha. Now, even though the root test is theoretically stronger, the ratio test is highly effective for specific problems. For equations involving factorials, the consecutive terms cancel each other out cleanly, bypassing complex nth roots and rapidly resolving our limits. Let's define what that radius of convergence actually means. This visualization shows a 2D complex coordinate plane. The radius creates a circular boundary around a center point. Any value we plug into our series that falls strictly within this boundary is guaranteed to converge. Here is the practical summary of everything we've covered. The root test provides greater theoretical power and easily handles sequences that oscillate. The ratio test sacrifices some of that theoretical reach in exchange for raw computational speed when dealing with factorials. True mathematical maturity requires recognizing these constraints. It means understanding the fundamental limits of each theorem so you know exactly which tool to deploy for the problem in front of you. If you found this breakdown helpful, be sure to like and subscribe to the channel. We'll continue exploring rigorous mathematical analysis in the next lesson.